Okay, thank you. I'll explain that. First of all, thanks to the organizers for having me and for the pretty great workshop and the program so far. Right, I'm going to present joint work with Felix Dellinger, Dennis Polly, Christian Müller, and Nina Smeenk. And okay, I give a disclaimer right away. None of these people does probability. So there will not be probability in this talk, but we work with an object from, well, discovered by probabilitists. And also, it's a discrete talk, right? We do discrete geometry. So I just want to manage expectations. If you're going to wait for 50 minutes for a limit, it's not going to come. Yeah? That's going to do discrete stuff. Right, but I think we can do some nice things in a discrete setup. So what is the goal? Well, we want to identify a special class of S-embeddings. I'll explain what an S-embedding is in a second. This is an object from statistical mechanics used to study the Eating model. And we want to relate that to discrete maximal surfaces in Lorentz space, in R21. How do we do that? Well, we heavily lean on two previous papers. First, there's this work by Dima, Mariana, and Benoit, which I will just call CLR from now on, where they introduce Lorentz lifts, essentially, for T-embeddings and S-embeddings. And the other thing that we lean on is from discrete differential geometry, from Sasha and Tim Hoffman and Boris Springborn, a paper about discrete minimal surfaces in Euclidean space. And what we sort of add is, we add geometric interpretation to this story, a bit of geometry to the Lorentz lifts. And okay, we translate this from Euclidean story to Lorentz space, which is not too hard, but you need to do it. And then we add a link, sort of, we relate those two things, and then we see what we can do. Yeah. I also, if you have questions, ask anytime, slow me down. I assume not the whole audience is surface specialists. So if you have a question, probably other people have the same question, so just ask it. There's some slides in the end, which are really not necessary, so you can really slow me down. Okay, so let's look at the definitions. What is an S-embedding? It's a map from Z2 to R2, such that in each quad, there is an inscribed circle or in-circle. Yeah? So a quad is a unit square. You could replace Z2 with more general quad graphs, but it's not difficult, and I mean, it just makes the exposition more difficult, so we stick to Z2. Right, that's a picture of a S-embedding. So, and then there's this Pitot theorem that says if I have a quad with an in-circle, then I can look at the length, and the sum of two opposite lengths is the same as the sum of the other two opposite lengths. And you can sort of conveniently rewrite this into an alternating sum being 0. Why do I do that? Because I want to explain what Dima and co did, CLR did, which is they look at these S-embeddings and they lift them to R21. Yeah? The idea is that these lifts agree in the first two coordinates. So S is the S-embedding, yeah. But for the third coordinate, I integrate these edge lengths with alternating sign. So I start here, maybe at height 0, so the lift is just coincides with the S-embedding. Yeah, so the S-embedding is in the XY plane and the base plane. And the third direction is here. And then for the second vertex, I add, so the lift is up here. I add this length L1 in the third coordinate. Then for the next vertex, I have height L1 minus L2, then L1 minus L2 plus L3, and then finally I have L1 minus L2 plus L3 minus L4, which is 0, which shows that this construction closes. Yeah, so I really get a well-defined lift on my whole Z2. And then why do we do this in R21 and not in R3? Well, because in this way, the lengths of the edges of the lift, so these green edges have length 0, in Lorentz space, because the length is sort of length squared is this length squared minus this difference length squared, which cancels out and is 0. Right. And then CLR also showed that, well, they studied the Ising model. We won't need these variables for a while, but since it's about the Ising model, I give you the definition anyways. And one way to define these cluster variables or X variables that are more or less the weights, I mean, they are the weights that define the Ising model after some transformation. They are the quotients of Lorentz lengths of the diagonals in the lifts, so these orange lines here. And because 3D is not so easy to see in 2D, I've animated some of these pictures just to rotate, because I feel it gives you a bit better sense of 3D stuff. Right, so there's this Ising model attached to these S-embeddings, that's why they study them. And because it's in R21, I give a very short sort of introduction to Lorentz geometry. So how is it defined? Well, we have this indefinite scalar product that has a minus in the third coordinate. And that has consequences because now there are different types of lines and planes and so on, right? For lines, it's sort of clear. I have directions that are positive, like distances in that direction are positive. There are some directions that have length 0. And then there's these directions where the length is technically imaginary. You look at the length squared, it's negative. I'd probably sometimes talk about negative distances because it's somehow more convenient. You have planes that are space-like, where all directions are space-like. You have planes that are null, or called light-like, where there are light-like directions and space-like directions, and there are time-like planes that are particularly steep. So the red one in this picture, where there are all sorts of directions. And you have different spheres, also come in 3 types. A space-like sphere is the blue one here. It's a 2-sheeted hyperboloid. All tangent planes are space-like. That's the idea. You have these light cones, which are null spheres. All points there on this light cone have distance 0 to the origin. And you have time-like spheres, where the distances, or where the tangent planes are time-like, and these are 1-sheeted hyperboloids. And we'll use those the most. Right, and unfortunately, there's lots of different names for them. So I sometimes speak of light-like spheres as null spheres because of radius null. And like lines and planes are sometimes called isotropic. Okay. So now we add the first bit of geometry to the CLR construction. We claim or we prove that per quad there's actually a unique time-like sphere that contains the 4 edges of this Lorentz lift. Yeah? These time-like spheres are ruled surfaces. They have lots of lines in them, 2 families of these lines. You rotate them around the axis, you get the whole thing. And I hope you can sort of see this in the picture. These green lines are contained in this sphere. Right, so that already means we have lots of spheres per quad, or 1 sphere per quad. In total, lots of spheres. You can look at these spheres from above. Yeah, so completely from above. Then there's a hole in your sphere, and that actually projects to the incircle of that quad. And in general, it's sort of terrible to look at these spheres because they're non-compact. If you have many in one picture, you don't see anything. But if you look from above, you at least see something. Right. There's also light cones in the vertices of the lift, so null spheres. Just because if I look at one vertex, all the generators come in this 45-degree angle. They're contained in these null cones. And, just proving we can also do nicer pictures. Here's 4 quads, cut off hyperboloids. Here are the cones, right? And then there's some other geometric property about these spheres. And that is that the null spheres touch the adjacent time-like spheres. Yeah? Sort of see where red meets blue. See, you have actually the 2 edges of the lift, right? If you have a point on a time-like sphere, look at the tangent plane. It's actually going to intersect the time-like sphere in 2 lines, 2 null lines.
Sorry, what are the 2 spheres here? They correspond to.
So I have the red one is a cone at the vertex of the S-embedding, a null sphere, and the blue one is the sphere that belongs to the quad. They're touching. Yeah.
They're touching.
They are touching. Do you have a question?
No, I just said very touching.
Yes, they're touching. But they're not the only ones, right? You can also look at adjacent quads and the spheres of these adjacent quads. They're also touching. In this case, as always, they have two light-like lines in them. One of them contains the edge of the Lorentz lift. Same would be true for two adjacent null spheres, but I did not make a picture, sorry. Right, and now we want to switch a bit to surface theory. So we're gonna come to this paper of BHS, and first I'm gonna remind you a bit of smooth differential geometry. So a maximal surface in Lorentz space is a surface that has constant mean curvature 0. It's the definition of a space-like maximal surface. Yeah, there are no minimal space-like surfaces. The name makes a bit of sense. They have mean curvature 0 and so on, and follow the same equations. But if you have a minimal surface in Lorentz space, it's gonna be time-like. So, okay, it's not too bad, but we'll stick to maximal surfaces. Okay, don't worry too much about this one. An isothermic surface is a surface that has a conformal curvature line parameterization. I'm going to say something in a second. But we're really interested in that because every maximal surface is an isothermic surface. Yeah? So the main motivation is we look at isothermic surfaces because we want to look at maximal surfaces. Roughly, generically, the curvature line parameterization of a surface is unique. Yeah, it consists of the two sort of extremal directions of curvature at each point. At some point in your surface, you have some direction like this and some where it curves like this, maybe. They're always orthogonal. But they're not always conformal. Yeah? Conformal meaning that in both directions you sort of have the same scaling factor. Okay. Yeah, don't hesitate to ask questions. Oh yeah. When you talk about surfaces, you should show some pictures just by principle. Here's a Euclidean isothermic surface, a Euclidean minimal surface.
Go back a slide. How do we see that this is an isothermic?
You don't. No, I don't think there's a direct way.
Yeah.
Huh?
You do.
You do?
Yeah, these are curvature lines, yeah.
These are curvature lines, but can you see that it's
Because
conformal?
you see squares.
But do you see that it's conformal?
Yeah, because it's square.
Squares.
The faces are squares.
Yeah, okay, if you know about discrete theory. But, or approximately, okay. I guess you can see. That's a minimal surface, yeah. I don't know if you can see this immediately. And here's a Lorentz maximal surface. There's much less pictures of Lorentz surfaces. So I just took a second picture, a bit more complicated picture of a Lorentz maximal surface. Yeah, they can also look complicated. Yeah, they don't need to be so nice. This picture visualizes a bit, though, that you have these two curvature line directions where the curvature goes in opposite directions. And so you everywhere have these saddle points.
This was not conformal. This was not conformal.
It is.
Isothermic. Oh, it is.
Every maximal surface is isothermic, so
Every maximal surface
yeah.
is
Yeah.
isothermic.
I mean, it's not necessarily in this parameterization, yeah, but it's always an isothermic surface. Right, and now we want to get to the discrete story. And this is a story from BHS. Yeah? We've immediately translated it to R21. And what is it about? So by H, I will refer to this as isothermic surfaces, but it's essentially a collection of maps. Yeah? You have some space-like circles at the black vertices of Z2, right? We just partition Z2 into black and white vertices. So a circle would, for example, be here. And at the white vertices of Z2, we have time-like spheres. So here you see 4 of these spheres in this picture. At the faces, we have points, and now we have a constraint for all of them, namely that right, per face, I have 2 white vertices, I have 2 spheres, they touch in the point of that face. Same for the circles, they touch in the point of that face. So here is a point of that face. I mean, here would be a point of that face, you only see one circle, And they do it such that the circles intersect these spheres in an orthogonal way. Yeah? They have this orthogonal constraint, essentially. And in the end, we think of the surface as given by the centers of these spheres. Yeah? So I'll denote those by M. Right? They sit in the centers of these spheres, and we think of them as approximating the isothermic surface or discretizing the isothermic surface. Yeah, go ahead.
Can you say one more time? Where are the white?
So this picture is slightly confusing. I'm sorry. So I just draw another one. That's a white vertex for me. And here is a sphere. Black vertex, there is a circle, right? And in the face is a point, but such that this circle intersects this sphere in this point. Just the blue circle intersects this sphere here at this point where the red lines intersect. Right, we sort of recall that I said before, if two spheres touch, there are these two light-like lines in that tangent plane, which you see here. Good, more questions?
So just to verify,
Yeah.
both circles and both spheres go through this point?
Yes, and they are touching there, and they intersect orthogonally there. Like the circles intersect the spheres orthogonally there. Yeah.
Is it like you're constructing a sphere
Say again, please.
pattern? Are you constructing a sphere pattern in the Lorentzian space for the graph?
We're not constructing a circle pattern in that sense. It's a sphere congruence if you want, but it's not a circle pattern. The circle pattern will be somewhere else.
So a sphere pattern in the Lorentzian space.
I mean, I don't know a precise definition of a sphere pattern, but it's a collection of spheres that are touching.
What is the meaning of touching?
Oh, in contact, like that means two surfaces are touching if they have a point in common and have the same tangent plane in that point. That's generally the definition. Yeah, you can say in contact or touching. Yeah, I hope. More questions? Okay. So, as I said, drawing the spheres, if you draw many of them, you don't see anything because they're not compact. So I just draw the centers. So here's an example of a S-isothermic net. The centers are these black points, and I've drawn the circles. These are these green circles, right? Because of all the conditions, the edge is actually a tangent, and the edge that connects the centers is tangent to the circles. And now I'm going to draw the spheres anyway, sort of to demonstrate that we don't see anything, or not much at least. But I can change my perspective a bit and start looking like from the top and more until I think that's completely from the top. Oh no, now it's completely from the top. And you start to see these lighter areas, yeah, where one of the spheres is not present. So I can just highlight these circles. These are Euclidean circles. We refer to these circles as the smallest circles, like smallest in the Euclidean sense. Okay, now I forget again about these spheres, and now I can look at some tangents, and I get this picture. Yeah, and it's a small patch, but you see at least in the middle, you have an incircular quad, and you have it everywhere else as well. So really, the trick is just take an S-isothermic net in Lorentz space, project it down to the plane, and it's gonna give you an S-embedding. Yeah, so there's an immediate relation to S-embeddings. Right.
The green is S-embedded.
The green is the S-embedding, right? And the brown ones are the incircles of the S-embedding. Yeah, and the black one is what you see still from the S-isothermic net. And one can make this a bit stronger in the sense that if I have an S-isothermic net, look at the projection and then look again at the Lorentz lift, that Lorentz lift is actually going to coincide with the spheres of the S-isothermic net in the sense that if I look at one of these blue spheres that I get from the lift of the S-embedding, it's actually one of the spheres of the S-isothermic net. These edges of the lift pass through the touching points. They are contained in these generators in the tangent plane. The cones, didn't draw that, but you can see that one cone per red pyramid passes through the circle of the S-isothermic net. So there's a really close relation here. Questions here? Okay. Right, but I mean, is that true? Like, can I get every S-embedding like this? It's a natural question, I guess. The answer is no. And to answer that more concretely, let's look at the definition. So this looks like a normal S-embedding, but it's not. This is actually what we call an isothermic S-embedding. You see each blue edge is tangent to two circles, but we could look at the other tangents. Yeah? And in general, you'll not get anything reasonable. But miraculously, here you get a second S-embedding. Yeah? You start with a blue one, and now suddenly you have a second one present with the same in-circles. This is not the same Ising model, I can tell you right away. I don't know much more, so it's a bit mysterious what these two related Ising models are about. Right, and this is one-to-one. If you have an S-embedding like this, it lifts to an isothermic net. If you have an isothermic net, it projects to an isothermic S-embedding. Right.
What do you get in general? What can go wrong?
What do you mean?
Do you lose the incidence?
Yeah. In general, if you look at these four green isotangents, they will not intersect in a point. They will touch a common circle, so there's something there, but it's not the point.
Is that maybe some criticality condition of the Ising model?
That's a good question. There is some restriction on the Ising model that I will come to later, but then still I don't know what it means. But I can make this more precise. I can make more precise what I don't understand. Okay, so then there's another neat trick. Yeah, that is one of the main reasons we look at isothermic surfaces. That is, I can look at this so-called Christoffel dual. Yeah, so if f is my surface, then df essentially consists of the two tangent vectors. You integrate them, you get the surface back. But if you integrate some general two tangent vector fields, I mean, you don't get a surface. Still, here I'm defining a second differential, this f df star, which is essentially t df, yeah, but I divide it by the square of the length. And so I take a tangent vector, take the same direction, but divide by the square of its length, so it goes from, length to 1 over length. And then I have this plus minus, plus I use in horizontal direction and minus in vertical direction. So somehow I take the direction, but the other way around. And then one other cool trick from BHS is that you can do this in a discrete setup. And what you do is you take the radii of your spheres, replace them by the inverse of these radii. And so M, remember, were the centers of the spheres. dm is sort of the discrete tangent vector, so difference vectors. I take the same difference vector, I divide by this sum of radii, which is just the length that it was before, and replace it by the length of the sum of the inverted radii. Yeah? So the new length is 1 over r1 plus 1 over r2, and I have the same plus minus law for the directions. And the theorem that I didn't write is, this works. This gives you again the surface, which is the Christoffel dual surface. Here's a picture sort of visualizing this process around one circle. You see M1, M4 on the left is parallel to M1 star. Sorry, GeoGebra does not have a star, so it's a prime. But M1, M4, and the radii go to 1 over the radii from before. And the vertical directions are switched because of the minus sign. Okay. Right, and the lemma, just to make this clear, dual is also isothermic, and of course, if I take the dual of the dual, I can make it so that it's the original surface. Yeah, Christoffel dual is defined up to translation, but I can translate it so that it's the same thing. Right, which also means, by the way, we get a Christoffel dual of S-embeddings, which means we get yet another.
So the angle just being pi 2 minus.
Pi minus, yeah. Yeah, exactly. Just because of this plus minus thing. And that Ising model will also not be the same Ising model. Right. So now I promised maximal surfaces, so let's try to get there. A smooth isothermic surface is maximal if the Christoffel dual is the Gauss map of the original surface. Yeah? Gauss map meaning normal map, so the normal vectors to the tangent planes to the surface. And another trick from BHS, they use this to define discrete maximal surfaces. And you say, okay, I look at the isothermic surface, I take the Christoffel dual, and if all the circles are contained in the unit sphere, in the Lorentz unit sphere, remember this two-sheeted hyperboloid, yeah? Okay, we want that it's in the upper half of that two-sheeted thing, then it's a maximal surface. Okay, this needs a bit of explanation, yeah? So, I mean, it makes sense that if all the circles are contained in the unit sphere, I have a picture, I think. Here's a picture, that this is some sort of Gauss map, yeah, because it's in the unit sphere. The green circles are actually the circles that are in the unit sphere. The blue circles are the intersections of these time-lag spheres with this thing, yeah. If I draw the spheres, you don't see anything, so I just draw the intersections. And, okay, but why is this dual actually like the normal net of the actual surface that we started with? Because there's another lemma that says, for a maximal surface, yeah, if the dual is in the unit sphere, then I can look at the centers of the circles. They're going to be contained in a plane. And that plane will actually be normal to the point. We have a dual point for each of the centers of the spheres. And so that direction in the unit sphere is actually a normal vector. Yeah. Just so you're not sort of misled, right? Orthogonality in Lorentz space works different than in Euclidean space. In Euclidean space, sort of perpendicular. But in Lorentz space, that's only true if the plane is parallel to the base plane. If it's tilted, then the normal vector will tilt towards the surface. So maybe if you're asking why does it not look orthogonal, it is orthogonal, but it doesn't look it. Right. So and together, that makes this definition reasonable because automatically, if the dual is in the unit sphere, it's automatically a sensible normal of the original surface. So this way, we have a discrete version of maximal surfaces. Right, and one nice thing about maximal surfaces is that they're in bijection with orthogonal hyperbolic circle patterns. Why? Okay, let me explain this picture. So this picture is the one I had before, except without the sphere. These blue and green circles are all in the sphere. The sphere has a lower part. In the lower part, I have a north pole. I do a stereographic projection from the north pole. And if I do that, the whole image will be contained in this disk. And I mean, this is how you construct the Poincaré disk model of hyperbolic geometry. And the circles will be orthogonal because they're orthogonal up here, and stereographic projection is conformal. They're orthogonal up there because that was a restriction to my isothermic net at the beginning, that spheres and circles are orthogonal. And there are variation principles for orthogonal hyperbolic circle patterns. Yeah? I'm not going to go into detail about this, but you can get these maximal surfaces from variational principles. Actually, the hyperbolic variation principles are quite nice. You get uniqueness and existence under some constraints on the combinatorics. Uniqueness is if you prescribe something on the boundary. What you don't, I mean, this story is older than S-embeddings, I think. You can definitely not prescribe the X variables. You cannot prescribe the Ising model. You prescribe the boundary and then you get some Ising model.
Sorry, Niklas, could I ask a question?
Always.
An orthogonal circle pattern is a conformal notion, so what does hyperbolic really mean?
It doesn't mean much, except that if you want to sort of get to the boundary, you could look at infinite orthogonal hyperbolic circle patterns, for example. Then you have to be careful, and also if you look at the variational principle, and the boundary conditions are about angles at the boundary, and so in this case you look at hyperbolic angles at the boundary. But otherwise, you're right. I mean, if I remove these disks, it's such a standard orthogonal circle pattern. Right. And okay, first, maybe more questions. Even basic questions.
What are the using variables in terms of just the circle pattern?
I don't know. It should not be hard to check or to calculate. Problem is there's a lot of things that should not be hard to calculate. So
Can you remind us where the
Yes.
graph is for the Ising model in this picture?
Yes. So each blue circle corresponds to a quad of the Ising model. So essentially the double graph of the black edges you see here is the quad graph of the Ising model. Sorry, I make this more precise. Each blue circle corresponds to an edge of the Ising model. So the graph of the Ising model sort of lies diagonally in here. It's like every second of the orange vertices.
Every other orange.
Yes. Yeah. More questions? Okay. Then I'll go to something slightly intriguing and maybe also slightly beautiful. Maximal surfaces do not come alone. They come in families, and this associated family. Phi is some angle I can choose. I define, I fix phi now. That gives me one surface. And I define it in a differential way. And what is this J? It means I rotate by angle phi around f star, which is the normal map for a maximal surface, right? So I look sort of at the point in my surface, the tangent plane and so on, in curvature line parameterization, the normal vector, then I just rotate it a bit. And then I integrate again. And then it closes again. This is special for maximal surfaces, yeah? It's of course not working in general. So, and then PHS also looked at that and have a discrete version to define this associated family. And the formula is essentially exactly the same. You just need to understand what am I doing here. Yeah, it's been a few slides since I used this notation. This quad means I look at the point where the circles and spheres intersect. On the unit sphere, that's, for example, where the circles are touching. Yeah? Two adjacent circles are touching, and they're touching on the unit sphere, so it's really a point on the unit sphere. And it's like my edge normal vector. And it makes sense, I want to rotate a discrete edge, I should rotate about an edge normal vector. And again, this closes. Yeah, this is somehow very nice, I feel. And that means we could also look at what happens to T and S embeddings, right? But there is a problem here, because in the associated family, doesn't matter if smooth or discrete, you're not in curvature line parameterization anymore. And the notion of S isothermic nets actually discretizes surfaces in, like isothermic surfaces in curvature line parameterization. Maybe I should show you a picture when we're at it. So these are 4 circles in an isothermic, in a maximal net, right? If I start out, at the beginning it's actually a maximal standard in curvature line parameterization. And now this is not, I'm not rotating my view, I'm actually rotating or changing phi. So it's the tangent vectors that rotate. Maybe you can see that here, for example, the green circles, they're not touching anymore in the sense that they have the same tangent vectors. They still have to only have one point in common and the sort of skew touching the quad, but this is not an S isothermic net in the previous definition. You see that maybe that these red vectors are staying in the same direction. So the normal vectors are fixed. Right. But that somehow means we should not be able to get S embeddings here, because there's no reason to, at least. And really we did not expect it to. However, there are some things one can do. So I don't want to explain something here in full detail, so I'll just explain it shortly. This wasn't a plan, but actually Dennis' poster outside. Yeah, Dennis, one of my courses, is here. Explains this. One can generalize this construction that we do for S embeddings to T embeddings. Like CLR have a generalized lift, however it goes to R22. We add a bit of geometry and can go directly to R21. I don't know if I should explain what the T embedding is, because the previous talk had that. But it's a circle pattern, we look at the centers. So the violet thing is a T embedding. And sort of what I want you to I don't know, Z is that, or understand is that, but this happening is that all these null spheres that we had in the vertices of the S-embeddings, they start having an actual radius, and that's the main difference. Otherwise, all these touching relations of these spheres remain. But now somehow we don't have null spheres, yeah.
So for S-embeddings in general, the left is one-dimensional, whereas in general,
yeah.
I think it's two-dimensional. So you construct a new one-dimensional lift
yeah.
of general T-embeddings.
Yes, by using spheres. But it's not something different. Yeah, it's a geometric interpretation of the CLR thing. We need Laguerre geometry, but because I don't want to explain Laguerre geometry, I'll not explain how this works. Yeah. Right. So why am I telling you this at this point? Because it turns out if you rotate in this family, in this associated family, you actually get lifts of T-embeddings. Yeah, so this is the starting point. It's an actual S-embedding. Here you can imagine there's circles of radius 0. Yeah. And now if I go through the family, I get red circles there. And these red circles have actual radii. Yeah, it's to be honest, I still don't understand why. Like, we can prove this, but I wouldn't say we understand this. And we prove it by calculation, which is, yeah, if we had another way, maybe we would understand it. It's sort of nice pictures, and then we were already very happy. But then at some point, we realized something, numerically at first, yeah. If you look at these red circles, they actually all have the same radius. I mean, over the lattice, yeah, or over the map. It changes with phi, it's just the sign of phi. Again, we can prove this and not understand this. And what this means is we can sort of compensate with this radius. Yeah? We have these circles of the original S-embedding. I mean, in this picture, the blue radii are constant, and the red as well, although that's less obvious. And so we sort of increase and decrease all the blue radii so that the red radii stay 0. And then we get this picture and this theorem. So here is an associated family of S-embeddings. At least a small part of it. Yeah? And it has the same centers as the thing before, because we're just changing the radii. Okay, just a conjecture up front is that this actually in the family is the same Ising model. We haven't proven that. Calculations, it should be possible by calculation, but it's a bit more harder. Okay, we have a long list of conjectures, so I want to sort of apologize. We have lots of things that are trivial that we did not prove, just because there is so many trivial things that you can probably prove, and we would never end, probably. And at some point, we wanted to present it. So, and in relation to this not changing Ising model and to maybe Rick's question in the beginning, we want to look at, or define something that we call the isothermic subvariety. Yeah? Which is a constraint on the x variables that define the Ising model. Right, recall we had these x variables in the beginning that are ratios of diagonals, or lengths of diagonals. They are associated in the terminology of the S-isothermic nets to the white vertices. So I'm introducing this. The defining equations look like this, but I don't want to show you them, or like I don't really want to explain the structure of these equations. I will explain how you get them. So essentially, I'm going to give you an instruction to derive them yourself, and then make sure yourself that you don't make mistakes and so on. And we need something more. To do this, we need Michael dynamics. I think that was an idea by Rick, who somehow conjectured it has something to do with dimer model, which I think still, I mean, I don't know how we came up with this, but it turned out to be true. So what is Michael dynamics? We have circle patterns. Just to make it clear, the red circles don't change, but the blue circles change. How do they change? I look at one blue circle, it goes through the intersection points of the red circles there, but then there are 4 other red intersection points. The new blue circle will pass through those intersection points. It's Michael's theorem that is possible. We could do many steps of that, but we only need one step, so that's the picture. So what does this have to do with our isothermic subvariety? Well, okay, let's recall. That's an isothermic S-embedding. Yeah? It has these 2 S-embeddings at the same time. There is, an S-embedding is a special case of a T-embedding. I think we had that in one of the lectures, but not in the talks. So you'll just have to believe me. But the centers of the black circles are at the vertices of the S-embedding. The purple circles have the same centers as the in-circles, but they are not the in-circles. Yeah? And the black circles have a very special property. They're touching, right? In the sense they have only one point in common. So if I want to replace the purple circles, nothing would happen, yeah? Because the adjacent black circles, they have only one intersection point in common. So it's like a local stationary point. Yeah? But I could, of course, try to replace the black circles, because the purple circles have other intersection points. So that's the red circles are the other thing. I know it's hard to see something here, so just believe me. And if I forget about the black circles, I'll actually get the other S-embedding. To compare here, maybe look at the blue thing, and it's the same here. Yeah. That's interesting anyway for geometry reasons, but it also helps us with the Ising weights. Why? Well, some people have derived formulas for these x variables under Michael dynamics. Yeah. And that showed that these formulas are these cluster mutations or this change of phase weights under space spider moves in the diamond model. Yeah? And actually, we don't have general diamond models because we're in the Ising model. You actually can get these subvariety formulas for the Ising model from this condition that the Michael move doesn't do anything to these variables. And because we have two S-embeddings, we sort of get condition here, a condition here, and we get in between a step how to transform these variables. So maybe I'm going to show it very briefly, but these formulas capture that. Yeah, this is the first Ising subvariety. This is how to get from one set of variables, diamond variables, to the other, and this is the second Ising subvariety. In consequence, that means you look at, I think it's 4x4 patch of Ising weights, and they satisfy some constraint. Yeah. That means that's a pretty strong constraint. In the end, it means you can only choose boundary data for the Ising weights. Then the rest is determined. That is somehow what we would, or from a surface perspective or integral systems perspective, that's what we would expect, because isothermic surfaces do not have local degrees of freedom. They should be determined by their boundary. Yeah, questions? Right. What we can show is, what I try to explain is that the x variables of an isothermic S-embedding are in that subvariety, but it's not true the other way around. Just because I have an S-embedding with x variables in this subvariety, they're not necessarily the projection of an isothermic net. Oops. However, I want to explain a bit more. So there's this conjecture that, can do simulations. We're very sure this is true. The x variables in the associate family are constant. And I also said before, this is a conjectural counterexample, right? Because I said in the family, we don't live to S isothermic nets. So that's an example where we would have an S-embedding that's not isothermic, that has variables in this subvariety. However, I also said that in the associated family, the nets are not in curvature line parameterization. So that means the name is maybe not so wrong, because they are still lift, so this counterexample still lifts to isothermic surfaces, just not in curvature line parameterization. Which means you can ask several reasonable questions here. You can ask, maybe does every S-embedding with isothermic x variables lift somewhere in the associated family? Could also ask, maybe it just lifts to an isothermic net in arbitrary parameterization. You could also ask, maybe not every S-embedding is like that, but maybe every Ising model is realizable as an S-embedding that lifts to that. There's lots of questions there. Okay, so my last serious slide, in my last 3 minutes, I think. Transformation behavior. Yeah, I'm sorry, that's a bit more geometry, but I think this is interesting. So we started out, let me explain the geometry a bit. Lorentz geometry, right? Geometry of R21, isometries of R21. Conformal geometry, you would maybe know from the Euclidean setup. We allow inversions in spheres, right? In 3 space, it's quite rigid. You can do the same thing in Lorentz space. You allow reflections in spheres. Lie geometry is somehow about touching spheres. Yeah, so there's there's a reason why we expand here, because we have touching spheres. Lie transformation is a slightly bigger transformation group that just preserves contact between oriented spheres. Yeah. And Laslier geometry and Lie geometry contains this as a subgeometry. It also contains Laslier geometry, which in the language of CLR is just this R22 model. Yeah? The isometries of R22 would be Laslier transformations. And I want to mention a few things. So maximal surfaces are invariant under Lorentz motions. S-embeddings turn out to be invariant under conformal transformations. And the same is true for isothermic S-embeddings. Yeah? And then there's T-embeddings, actually. So we generalize this slightly, but it follows immediately from the CLR construction, are invariant under Lie transformations. I mean, like as surface theorists, at least in Berlin, maybe Vienna, we love Lie geometry, and now we maybe have a reason why we should do it more. So I'm very happy about this. Yeah, they preserve lifts of T-embeddings. Apply a Lie transformation to the lift of a T-embedding, it's still going to be a T-embedding. And then there's something else that CLR showed. If you look at the X variables, they're actually preserved under these Laslier transformations. And this is a bit of a mismatch, I feel, at least. Yeah? Because the S-embeddings are over here, and the isothermic stuff is over here, but the X variables are on this side. In particular, the X variables would not be invariant here. And then I can apply a Laslier transformation to the lift of an S-embedding. It will be a lift of a T-embedding that has the same X variables, but is not an S-embedding. Yeah, so I don't know. I have some suggestions, I guess, how to fix this. First, there's a bit of advertisement, because I have a preprint explaining how we can also associate conformal X variables to circle patterns directly. That would be in the plane, invariant under conformal transformations, and behave the right way around under Michael dynamics. But okay, I cannot make any probabilistic statements about those. But they would, and conjecturally, they fit quite well into this picture on this side of the story. On the other hand, there are some people who study L isothermic, so Laslier isothermic nets, both in the discrete and continuous setup. I don't think there are LS isothermic nets, but maybe one could do research in that direction, and maybe in the end we want to match up those two and those two. I don't know. And of course, you could also ask if there are maybe variables that are invariant under Lie transformation, some sort of Lie variables that would be maybe even more natural. And now I'm out of time, I think, right? Okay. But this is sort of just motivation, because we had some very nice, I feel, some very nice talks this workshop about incidence geometry. And our original idea actually was to take this R22 lift of CLR, do stereographic projection to the Plücke quadric. This is higher dimensional stereographic projection. Plücke quadric actually, what is it about? It's about lines in 3 space, projective lines in projective 3 space, or 2-4 Grassmannians. Yeah. So you can start with a T-embedding. There's a whole dictionary to identify T-embeddings with some sort of configurations in projective 3 space. There is even a way there to see all these T-graphs in a geometric way, as certain. We intersect the configurations, the lines in your configuration that you get with a plane that goes through a special line, and then you get the whole family of T-graphs. So I don't think it helps with anything, but it's nice. S-embeddings are a special case, and not an unknown special case, which coincide with these so-called discrete linear line complexes studied by Boubenko and Schief. They already figured out there that there's some relation to the Ising model, at least to an Ising model maybe with complex weights or with non-positive weights in general. But if you would do it this way, you would end up with specific line complexes that would have positive weights. Why did we give this up? Because we want to have something like maximal surfaces, and I have no clue if this means anything in terms of surface theory. Yeah. Anyways, but if you're interested in these incidence stuff, then maybe this is a link that you should look at. Yeah. You can ask me about it later. Right. And that's it. Thank you very much.